Hello, everyone, and welcome to our presentation today on safe piping matters, material considerations for plumbing systems. And AIA members, all of you will get a learning unit and HSW. So welcome Paul Hagar, who's the Executive Director of Safe Piping Matters. And we look forward to hearing what you have to say. Over to you, Paul.
Great. Thanks, Tara. I appreciate it. So as Tara said, my name's Paul Hagar, and Safe Piping Matters is an organization that works to inform the building trades about important issues related to plumbing and piping systems. I just want to start by saying thank you to everyone for showing up. I'm actually glad it's a small group because I was telling them the first time I've gone through this presentation, so hopefully I won't stumble too much and won't run too long or too short, but we'll see. So it's going to be a little bit of an adventure. Here's the required AIA provider statement. I'm sure you've seen this before. I do want to take the chance now to just really ask for your feedback on this presentation. A lot of the info and issues that we're going to talk about today came out of discussions with people like you. So we really appreciate any ideas, suggestions, comments. I'll put a link in the chat later so that you can just fill out a form. It's going to be like 4 questions. So here are our learning objectives. And over the next hour, or really 45 minutes, we're going to assess the strengths and weaknesses of various piping materials by looking at their product life cycles, health impacts, and covering some safety factors, including issues like permeation, fire risks, and fire stopping considerations. So getting started, we all know that plumbing and piping systems contribute in many ways to building performance. And today we're going to focus on some important issues that don't always get the focus they deserve. A lot of times discussions just center on cost when it comes to piping. And sometimes it doesn't get much thought at all. A while back, an architect told me he spent more time thinking about urinal dividers than he did on piping. And that's understandable, but it's not really what we want to hear. So your key takeaway is this: piping materials do matter when it comes to health and safety in buildings. We're going to cover the information today by going through 4 main sections, each of which is going to have a few different topics. So we're going to start with a quick overview, just looking at plumbing systems overall and kind of orient you to what we look at. So the 3 applications we look at for piping inside buildings, not piping in the general infrastructure, but inside buildings, is water distribution, so for drinking and sanitary use, providing drain and vent systems for waste disposal, and reducing risk from fires with sprinkler systems. There are obviously other piping systems that are in buildings, like gas distribution for heating or med gas or stuff like that, or wiring conduit in commercial buildings, but we're not really going to talk about those today. So starting about piping materials, we focus on these 3 mainly. Pipes made of copper, which are used mainly for water and gas, pipes made of iron and steel, and pipes made of various types of plastic, and they're used in a bunch of different ways in buildings. Each one of them has its strengths and weaknesses, as the chart shows, including different levels of stability, resilience, and overall performance. So we're going to break down the details in the rest of this presentation. So before we do that, I want to add a 4th box, which shows 2 obsolete plumbing materials: pipes made of lead and pipes made of polybutylene plastic. These pipes are no longer used, or no longer installed anyway, and are being replaced wherever they are identified. Why we look at those as well is for the lessons that they can teach us about what happens when piping materials turn out to be failures. Starting with lead, there's been a lot of attention over the last 10 years or so as various communities struggle to deal with the toxic impacts of that plumbing system. And polybutylene pipes had their own day of reckoning in the 1990s when the material became brittle and failed due to weaknesses in the material itself. First, I also want to talk a little bit more about plastic and plastic pipes, because there's many flavors of this, as I'm sure you all know. CPVC, PVC, HDPE, and PEX are the main ones we look at. You can see little tiny pictures of them there and kind of how they're mainly used in buildings. Why it's important to separate these out is that they all have their own sets of characteristics and pros and cons. So we're going to break out those a little bit and talk about them through the rest of the presentation. So starting out with sustainability, we want to take a look at this with regard to piping systems, because first of all, sustainability in the building and construction sector is important. You've probably heard that our sector is responsible for 30 to 40% of the world's energy use and emissions. We also should be aware that we are a huge source of waste generation in the world as well, with, for example, thousands of tons of plastic waste alone being generated every year, making the construction industry behind only packaging as a contributor to plastic pollution in the world. So if we want to keep moving toward sustainability, we have to keep improving how we design and build homes and workplaces. What the heck does that mean for pipes? The UN has, of course, been looking at the issue of sustainability for decades, and in 1987, they defined it in a pretty nice way. I think it's a way that maybe doesn't focus as much on technical aspects, but just says sustainability is doing things now that will make sure that people in the future can continue to live healthy and productive lives. That means we got to move away from linear processes where we're just creating stuff and producing trash at the end, and towards circular processes that reuse resources and have smaller carbon footprints. So to understand what that means for piping, we have to look at what that means at every stage of their life cycles, from production through installation and use, all the way to disposal and afterward. By the way, I'm just going to pause here for a second and just say, if you have questions, just unmute and please ask, because again, I would love to answer or clear up anything that doesn't quite flow in this. So we're going to start with copper. Copper is one of the oldest plumbing materials. It is the oldest plumbing material in the world. It's been used for centuries in plumbing. And like all metals, its production does impact the environment. You disrupt the areas around mines and you generate lots of waste products. And refining the ore into ingots and then making products out of them also uses a lot of energy and generates a carbon footprint. So as we'll see in a minute, though, once that copper is made, it can be used again and again. Major copper producers have committed to transparently reporting against UN Sustainable Development Goals through a program called Copper Mark, which we're tracking. This requires them to reduce the negative impacts of their operations over time. So not an A grade, but not an F either. In use, copper piping performs pretty well. It lasts decades, which is great for sustainability because you're not replacing it. Often it'll last longer than the life of the building in which it is installed. The metal is resilient, it's stable, and one of the nice things about copper is, well, it requires training to do. The fact that you can solder and braze copper means that you can actually repair it without having to just rip it out and put in new. So, and as mentioned a minute ago, at the end of its use, copper pipe keeps its value. So that goes beyond just financial worth. When buildings are demolished or if they're refurbished, that copper scrap that gets taken out doesn't go in a dumpster. It goes into a recycling bin, it gets resold, and it retains all of its strength, its stability, and its formability. So copper used in Roman times is basically the same as what we produce today. And studies estimate that about 2/3 of all copper ever extracted is still in circulation. So reusing these resources not only lowers the need to extract more materials, it also greatly reduces the energy needed to make new pipes or new products of any kind. So analysis shows savings of about 85%. So that's kind of what this graphic on the right, is meant to illustrate. So now we're going to turn to pipes made of iron and steel. We lump them together because they're pretty similar. The story for this kind of piping is basically the same as copper. Mining and refining it has impacts and produces a carbon footprint. In addition, though, the heavier weight of iron means that transporting it also extends the carbon footprint a bit. But like copper as well, the industry has engineered processes that are in place to reclaim the materials and use them again. So this is here on the right is a huge pile of cast iron scrap, which was at a plant up in Oakland, actually, which produces all of its cast iron pipe out of 100% recycled materials. That's pretty typical of cast iron produced in the US, by the way. So in use, iron and steel perform at a similar level to pipes made of copper. One advantage that iron has over basically all other types of piping material is the weight that we mentioned before, because that translates to a high level of structural strength. And that means that things like installations in parking garages or installations below grade, let's say they're under foundations or under roads or paving, that piping is going to withstand stresses that other pipes wouldn't do as well with. And at the end of its life, steel and iron pipe are, in fact, two of the construction industry's most widely collected and reused materials. Recycling rates stand above 60%, according to the Iron and Steel Institute. The price per ton varies a lot more than copper does. That's pretty consistent, but the value is still significant. So economic incentive to actually recycle it. So finally, let's look at plastic pipes. For plastics, the first part of the life cycle also has big impact. So plastic comes from fossil fuels. So that means you're drilling for oil or you're fracking for natural gas in order to generate the pellets that become feedstock for making these pipes and other plastic products. So plastic manufacturing has exploded over the past 30 years, and the UN projects that in 7 years, it will have expanded a further 5 times. So I guess that raises some questions. What does that mean for plastic's carbon footprint now and in the future? And what does that mean for plastic waste now and in the future? In use, the many types of plastic that we looked at before, sort of the 4 flavors that we mentioned, actually make it a little more difficult to ensure that they're installed and maintained according to what the manufacturers require to make sure that they continue to operate well. Because plastic piping is combustible, for example, it has to be specially protected against fire risks. We'll talk a little bit more about that toward the end. And plastic pipes also need protection from chemical damage and physical impacts. So we'll talk about those as well. At the end of life, this is where the most significant difference of plastic pipes comes in. Virtually all plastic is engineered for single use. And the recycling rate for plastic pipes is close to 0%. So all that plastic gets landfilled, adding to plastic pollution, or it gets incinerated, increasing carbon and emissions. Looking at the materials, so then if you look at carbon, iron, steel, and plastic, it's clear that making any kind of pipe has an impact, right? How they stack up in the disposal phase, though, is the real area of difference. Copper and iron and steel are circular, plastic pipes are not. So let's look at health factors now. During use, plumbing systems obviously need to ensure water quality to protect human health and make sure that the waste gets out of the building, again, to protect human health. And research that we're seeing is tracking two issues that are related to human health. One is leaching from pipe materials into water, and a second one is the increasing aging of water inside pipes. So that's what we're going to talk about in this section of the presentation. So chemical interactions between piping materials and water, typically these are oxidation or chemical reactions between water or additives in the water and the pipe wall, mean that all pipes leach substances into water to some degree. Some materials, though, are far safer than others. So here's our poster child, that's the right word, lead. So toxic leaching from lead pipes and fittings has obviously emerged as a serious public health threat in homes, schools, and businesses with older plumbing. I was telling Tara before that that's a bigger issue on the East Coast than it is in the West. But cases like the lead poisoning incidents in Flint, Michigan, or New York, New Jersey, or Washington, D.C., or Philadelphia, Pennsylvania, or many, many, many other communities have affected the lives of hundreds of thousands of people for decades. Assessment and repair efforts are ongoing, and the recent Infrastructure Act is going to invest $15 billion to find and replace lead pipes. That, by the way, we estimate is about a third of what's actually going to be needed. So hopefully we'll get some more money put into that area somewhere. So the lead and copper rule sets the action limit for lead at about 15 parts per billion, but it turns out that no level of lead exposure is okay. Despite all that, we relied on lead pipes for centuries. People thought they were mostly safe, but it turns out that wasn't true. So the pipe materials most often used to distribute potable water must meet a standard called NSF ANSI 61. And the committee that produced this standard in 2016 flagged some important issues that we want to just pull out for you. First of all, they noted that water increasingly is sitting in pipes for longer than the standard tests for. So the longer it sits, the more leaching and microbial growth will occur. And second, they noted that the standards, they excluded from the standard requirements for how often a certified product needs to be retested. So that's an issue that creates a little bit of a loophole because some of the materials used for piping do vary quite a lot over the course of time. So we're going to take a quick look at what research shows on the leaching rate of various metal and plastic pipes, as well as some of the health impacts associated with those. So starting with copper again, this pipe material leaches a little bit of copper at levels that are generally safe, average 20 to 75 parts per billion. For reference, the EPA standard is 1,300 parts per billion. So it kind of tells you where gives you a relationship. So what this means that in general, people don't need to worry about the low level of copper exposure from water. In fact, copper can be good for you. So it can help with muscle elasticity. It helps with blood health. So I think there is a condition called Wilson's disease that means people can't flush copper through their bodies. Those people have to be very careful about their copper exposure, but most of us don't. Pipes made of iron and steel are a little different. In some cases, they can begin to corrode, generally after decades of use. In some cases, disruptions from construction renovation or from water exposure to water with higher acidity can accelerate the corrosion process. And that can lead to water becoming brownish because it has little rust particles floating in it. And it will also have a telltale metallic taste. So at higher levels, let's say if you were taking iron supplements or whatever, and then you had exposure to water that was brown, you probably wouldn't want to keep drinking that because it could create nausea or illness. So here's something you might not have heard. Leaching from plastic pipes has been pretty well documented. the plastics industry has often said that they're a better alternative because metal will tend to corrode. We did just note in some cases it does, or leach into water. But plastic pipe, plastic fittings, and the chemicals, solvents, and adhesives that are used to bond all these systems together contain chemicals, hydrocarbons, and other additives that are used to ensure good performance. These chemicals also leach from pipe walls over time, especially in plumbing that is exposed to heat or exposed to hot water. So in the case of hot water, this is a reason you can't use CPVC in hot water systems because it just can't handle it. It breaks down. So here's an interesting little thing I mentioned before, which is that plastic pipe formulations do change from factory to factory and even from batch to batch as the producers are adjusting their recipes to address performance issues. It's unclear how often they actually retest against NSF ANSI 61 standards to make sure that these different chemicals are remaining stable in the plastic wall. So we have a 2018 study from Gradient that looked at research across the entire industry and cataloged 163 leachates, including VOCs and SVOCs, that came out of all the different flavors of plastic pipes. Different blends from different pipes because they have different chemistries, right? Just one example, occupants of buildings with PEX pipes often report a distinctive, unpleasant, chemically taste and smell for weeks after these pipes are installed. So that's why a lot of systems will be flushed with lots of water before they are put into service to try and alleviate that. The leachates that have been identified include hydrocarbons, ketones, esters, phthalates, many of which have known detrimental effects on nervous systems, organ function, and the nervous system. Another troubling trend that we're tracking is that researchers are starting to see or are continuing to see sperm counts decline, and they have been declining since the 1960s. And this effect corresponds roughly with increasing use of plastic in our daily lives. We can't say how much of this comes from pipes, of course, but the additive effect is pretty clear. So now we're going to look at some health factors and within building plumbing systems. And this is an emerging topic of discussions in the plumbing industry, and here's why. Water engineers are increasingly finding that the water inside buildings is aging beyond the 24-hour cycle and the 19-day test period that is specified by NSF ANSI 61. So ironically, this challenge is exacerbated by increasing design of green buildings and low flow fixtures, which are saving water, but they're also saving water. So there's not as much water flowing through the system. This can be an issue with systems, particularly that are used only periodically. So think of schools that are idle for weeks during breaks or for months during the summer, or seasonal properties like, I don't know, ski condos or beach houses or whatever, or other facilities that just might sit idle for days, weeks, or months. Of course, poor design can also be an issue if you have dead ends or storage tanks that aren't properly flushed and maintained. This will also be an issue. What does this do? Increased water age causes a number of issues. And here's a nice illustration from Contractor Magazine that shows that. So the first issue is microbial growth. Disinfectant additives in the water degrade over time as the water sets in the pipe, and that gives opportunistic pathogens like a chance to grow. Research shows that even overnight, colony growth of pathogens increases by 80 times the initial level in just 24 hours. And if water is allowed to stagnate for 2 months, for 60 days, it goes up by 40,000 times. So you can imagine what that water looks and tastes like at the end of that process if the system's not flushed. A nice example of this is the spike in incidence of Legionnaire's disease that happened as we transitioned out of the pandemic shutdowns. So another issue is that water sitting longer in pipes also interacts more with the material in pipe walls, so you get higher levels of leaching. I mean, infamously, if you test lead pipes for contamination, water coming out of lead pipes for contamination after it's been flushed, it can have a low level, but if the water's allowed to sit there for a few hours, all of a sudden that level rises. So that's true of other types of piping materials as well. So to address this issue, the International Plumbing Organization, IAPMO, is recommending that we change the way that the diameters of pipes that are specified in buildings to provide smaller diameters so that you get increased volume as flowing through the system. We haven't seen, though, any difference among various piping materials in what one being better than the other. So, for example, unlike sustainability, where there's some pretty clear differences, we know copper has some antimicrobial properties, but there's no research anyway at this point that shows it's any better or worse than iron, steel, or plastic. So our last two topics that we're going to talk about relate to safety implications. We'll start with stability, strength, and permeation, and then we'll look at fires. So we're going to take a look at what happens when pipe materials are faced with accidents or incidents, so inside or around buildings. So some of our more serious issues come from chemical compatibility problems, which can occur from a few different sources. First, incorrect design and installation. So if you mix different plumbing materials together, they don't play nicely. So you've probably heard that, maybe even seen some issues, let's say in homes where DIYers or whatever didn't quite know what they were doing, and they ended up with lots of corrosion or pipe systems that just didn't work correctly. But it can also happen when, your average teenager who doesn't really know what they're doing, or normal people too, are not really aware that they shouldn't be dumping that boiling hot liquid, oil or whatever down the drain. And they probably shouldn't be putting those harsh chemicals down the drain either. So that can cause issues. And finally, they can occur as a byproduct of maintenance on building systems. For example, HVAC or other subsystems that are in plenums where piping systems are as well. So think of overspray from lubricants or drips of caulk or spray from mold or insect treatment or lubricants. If that gets onto pipes and that pipe isn't happy with that, you can have problems. So the issue with this particularly, and why it's more serious, is that a lot of times this damage isn't like the pipe's not broken, didn't freeze and break. So it'll just gradually deteriorate, and then all of a sudden everything's broken, right, throughout the whole building. We'll talk about an example in a second. So each type of pipe has different levels of risk posed to this. And so we're going to take a look at those. Some variations to consider are listed here, so I'm not going to go through them as much because we're going to circle back to them in a second. So again, starting with copper. Copper is generally impervious to corrosion, except if you're exposed to aggressive water. So you can see that in Southern California, Arizona, and Utah, especially if there's well water that's untreated, this can cause issues with copper pipe. It can create pitting or pinhole leaks. This occurs with water that has pH levels generally between 7.0 and 7.7 and a dissolved CO2 of at least 25 milligrams per liter. So if you treat the water and bring the pH into an acceptable range, you're not going to have this problem. But systems that don't test or treat problems, so again, well water, for example, where the homeowner or the small community water systems might not be treating the water to correctly, they might see issues with this. Cast iron and steel pipes, again, sort of behave similarly to water. They're actually a little more stable or resistant to damage from acid. You can go all the way down to 4.3 with a iron pipe, excuse me. And if you're below that level, codes require that you put in a corrosion resistant system anyway, for example, an epoxy coated pipe. So you're not really going to run into that issue in general. So repeating theme here, plastic also varies because they're different flavors, again, in its resistance to different types of chemicals that are going to cause damage. And that will happen with basic material types like PVC, but it also will vary within the category of PVC, for example, with various subtypes having different levels of performance, making them acceptable. Some PVC you can actually use for potable water. Most PVC you can't. Manufacturers of these pipes list literally dozens and dozens of substances to avoid, and they list them by their chemical names. So you don't really know what's in the stuff. Like, where am I going to find a ketone in my maintenance closet? So there's just far too many for us to go through today, but I'll give you some general list of some issues to think about and to research with regard to particular pipes. The speed and degree of damage that occurs for plastic varies, like we said before, by the concentrations present and by relative temperature. So if it's warmer water, warmer liquid, warmer air temperature, you're going to get more reaction. The bottom line here is that your construction teams and your maintenance teams for the ongoing operation of the building have to work closely with, or at least know what the plastic manufacturers require if they want to avoid causing problems. So here's a summary of some of the things that can affect the integrity of plastic plumbing systems. Chemicals used for termite treatment and mold abatement, caulk, solder flux, spray foam insulation, HVAC chemicals, fire stopping products, thread sealants, primers, cleaners, even some oils and detergents can cause issues for plastic pipe. And this can lead to things like plasticization, where the structure of the pipe breaks down, or it may cause the pipe to become brittle, so it's more easily cracked or broken, or it could actually create stress cracks in the material itself. So just the weight of the pipe then might cause it to crack. So even things like exposure to sunlight or UV light of any kind can cause surface degradation and increased risk of breakage. We mentioned before the hot water issue with CPVC, that's excluded by code, but I just mentioned it. One thing that we saw last year was that a computer contractor had installed his computer wiring alongside of plastic pipes running through walls. So there was already a hole. You can see what he was thinking here. There's already a hole in the wall. Let me just lay my Cat5 cable on top of it. The problem was that the sheathing of the Cat5 cable has plasticizers in it, so it can, sort of bend and whatever. Those plasticizers ate away at the plastic of the pipe and created little wormhole-looking holes in the pipe itself, and you had lovely leaks. So plastic pipe manufacturers publish a lot of documentation on what to avoid. So, but this is a high-level summary. The basic structural strength of pipe materials is obvious that we need to consider it in certain building applications within buildings. So for areas where risk of damage might be higher, such as parking garages or high traffic areas inside buildings, manufacturing floors, under foundations or paving, engineers and architects really need to consider materials rated for higher crush loads in those areas. Note that cast iron is most resilient. Plastic pipe with cellular core has the lowest crush rating. Thermal expansion is another form of stress that is placed on piping materials. So expansion and contraction as temperatures change on long pipe runs can affect the fidelity of joints and fittings, and of fire stop brackets and fasteners, which we'll talk about in a second. Cast iron pipes, again, perform best here, followed by steel and copper, and PVC and PE react more to temperature changes. So what that means is that architects and engineers need to account for these thermal expansion and contraction factors when they're installing long runs of pipe in unconditioned spaces like exterior walls, shafts, soffits, light industry that's maybe not heated or cooled to the same level as normal office or residential space, because they're going to experience larger temperature swings during the course of a day or in temperate climates from different times of the year. So now we're going to turn to an issue of permeation. Piping that connects buildings to water mains often passes below ground. This puts them going under streets or through soil that might contain environmental pollutants like gas, pesticides, industrial waste, other chemicals. Research shows that many of these commonly used pipes will allow substances to pass through the piping walls. This process is permeation. So what happens is basically the material goes into the pipe wall, it gets absorbed into it, it then diffuses from the pipe wall into the water and affects the quality and safety of the water inside. It can also, by the way, compromise the structure of the pipe itself. Think back to those chemical compatibility issues that we talked about before. So the EPA says risks from permeable pipe are limited to plastic, non-metallic materials. This is because they are inherently just more porous than substances like copper, iron, and steel. So in general, this is due to the lower density of the piping material. So again, the implications for design and construction are that buildings that are located near manufacturing facilities, gas stations, agricultural locations, all of those should consider whether they face ongoing risks from leaks or spills, and specify piping materials that, if needed, are resistant to permeation. I want to pull out an example just from last week, though, East Palestine, Ohio, which illustrates that any location can be at risk if an accident occurs. So you had a huge spill of vinyl chloride. This is a major component of PVC pipe, that's the VC. And those folks that are in that community are going to have to be pretty careful and vigilant over the next weeks or months as the pollutants that are definitely in their soil and potentially moving into their aquifer go through their system. It's not just a matter of testing now and next week. They're going to have to keep doing this. Other examples that apply here would be the spills of jet fuel near Pearl Harbor in Hawaii, which affected like 90,000 people. Or in 2018, there was a big industrial spill outside Charleston, West Virginia that affected about 300,000 people, where a additive got spilled into the river and then got into the aquifer. So, okay, so we're almost at the end now, which is thank God, because we're almost running out of time. So we're going to end by discussing how piping systems can affect the safety of buildings, occupants, and first responders in fires. Various types of materials perform quite differently, and that all comes down to one thing, basically. It comes down to combustibility. So here's a chart showing temperatures at which different types of pipes will melt and catch fire. As a point of reference, the average structural fire is about 1,500 degrees Fahrenheit. So metal pipes are not combustible at 1,500 degrees, although of course they will melt when exposed to very extreme heat, like in a factory or whatever. By contrast, we can see that plastic pipes do start to burn at temperatures much lower than happen in a fire, starting as low as 400 degrees, Fahrenheit. Some plastic pipes also will melt before they burn. So that's the ones listed up here, PE and PVC. Others just go straight to burning. So that can cause issues, including failures. Mostly they start in exposed spaces or walls. And then there's also issues that we mentioned before where heat can create chemical leaching from pipes. So here's a couple examples of plastic issues with fire. Santa Rosa, of course, these some images that a news outlet took after the fire, showing that they installed a plastic pipe above ground for their water supply in a wildfire-prone area. So that didn't work out well when it actually did burn. What happened was that the people served by this pipe, miles of it burned. The people served by the pipe were without water for months. And even after the system was rebuilt, it turned out that benzene had contaminated their water system, leaching from the melted and burned pipes. So you had now contaminated systems that were continuously releasing benzene into the water. So ultimately, that had to be replaced and repiped. Confusingly, the water system here chose to again install plastic for this supply line when they replaced it. I'm told this was a value engineering decision. So we can ask questions about what will happen the next time a fire happens in this wildfire-prone area. The Grenfell Tower tragedy in London represents, one of the best known examples of a building tragedy related to burning plastic. The plastic composite panels here not only increased the heat of the fire, but they helped it spread up the building as it burned. 70 people were tragically killed in this incident. And actually the fatalities are continuing. So 12 firefighters were just reported to have died of cancer since the Grenfell fire. It's thought due largely to exposure from smoke, toxic smoke there. When I was at a recent conference in London, a colleague relayed the depressing news that the building industry in the UK so far has failed to question its choice of materials. And they're seeing actually the use of plastic increasing in buildings rather than decreasing. So we're running short on time. I'm going to just quickly go through these next ones. This is a super illustration from research showing why combustibility matters for structural fires. The Fire Safety Research Institute, together with UL, produced a video. If you Google it, you'll find it right away. Showing how two different rooms were impacted by a burn test. The one on the left was designed with materials from the 60s, kind of looks like a room from the 60s if you look at it closely. And it's using things like wood, metal, and natural fibers, cotton, wool. The one on the right was designed with materials from the last 20 years. So you're talking about plastic laminates, you're talking about plastic foam inside the furniture, you're talking about polyester type fabrics. Despite the use of flame retardants in that room, the one on the right was fully engulfed in flame in less than 5 minutes. You can see even at 3 minutes and 48 seconds, you've got quite a large fire with lots of smoke coming out of that controlled burn test. The one on the left, the natural room, that was still not fully engulfed after 29 minutes. So imagine what that means for occupants of that home or that room, and how much time they would have to escape the synthetic room, and how much of a chance firefighters would have to respond in one versus the other. For pipes particularly, the chemicals that get released into smoke and into water are detrimental. Research has shown, you can see there are a couple of journal articles listed there, has shown dozens of VOCs and SVOCs being released into air and water and soot, plus even toxins like formaldehyde and hydrogen cyanide being released in the case of a fire when pipes melt or burn. Purdue professor Andrew Welton analyzed water samples out of the Paradise wildfire and found benzene at levels 40,000 times the safe limit, as well as scores of other chemicals with negative health effects. So breathing this smoke or being exposed to it has a lot of detrimental effects in the short term. Lung irritation, nausea, burning eyes. Long term, though, the NIOSH studies of firefighters have shown increased rates of cancer in the nervous system, the liver, the brain, and reproductive systems. Somewhat like the issues with sperm count, this correlation you can see in the graph corresponds roughly to the growth of use of plastics in buildings. So raises a question, should we continue to plasticize the environments where we live and work? We're running really short on time, so I'm going to fly through this a little bit. So you know what firewalls are, and fire stops are the barriers that restore the integrity of firewalls from penetrations from plumbing and HVAC systems, et cetera. If fire stops don't work, they might as well not be there, because research shows that even a pencil-sized hole in a firewall can allow enough toxic smoke through to fill an adjacent room in 4 minutes. So in order to work, every single fire stop system has to account for the specific materials and the specific situations they're designed for. Codes prescribe these, but in reality, the experts we've talked to say that they see lots and lots of errors in the field. We don't have time to talk about them all, but we'll quickly go through the most basic one, which is installation. So the image here on the left shows a large plastic waste pipe in the center that is fitted with a collar that should secure it to the wall, right? This is so that in a fire, the intumescent material that's installed around that pipe through the wall, when it heats up, it should expand, crush the pipe, and seal the hole, right? Because it's secured. The problem, though, is you can see here that the collar isn't attached to the wall. So when that foam gets heated and expands, it just takes the path of least resistance and pushes both ways out the wall, pushes the collar away, and leaves a large gap for flame and smoke. So that's one reason why combustible pipes aren't really allowed in hospitals, high rises, and other buildings where safety is critical. So we're coming to the end of our time, so I'm going to quickly sum up before answering questions. So materials used for piping have big impacts on sustainability before, during, and after their use. They affect health, and they determine how safe people and firefighters will be if a fire occurs. So I'll leave you with a couple thoughts. Remember at the beginning, we talked about lead and polybutylene pipes and the lessons they offer. So can we learn anything from what current research is telling us about the pipe materials we're using today to make buildings safer and more sustainable? Thank you again for letting me speak with you. We really appreciate the time. And if you want more details on these issues, please consider downloading our free plumbing specification guide. So that's shown here. And I'm happy to email you the link if you'd like. I'd also, like I said before, I'd love to get your feedback. And I will drop a link in the chat now if I can find it. Chat, yes. Great. So there's the link to the chat, or link to the survey. So I will open it up in case there's any questions. All right. Love it, Stephanie. Thank you. All right. So I'm just going to quickly, since we have a couple more minutes, I'll start the conversation. So sometimes I get the question from manufacturers asking, what should we be doing to improve our own sustainability? And our answer is to be transparent. So release the info on how you're doing things, what you're making products with, and the challenges you're facing. And the industry is pretty good at rallying to give feedback and helping find solutions. I think that's how, for example, iron and steel have gotten so good at reducing their impacts. I mean, they're still not great, but they're a lot better than they were when Pittsburgh was covered in soot, right? So they've made definite progress. So I would love to see that happen for more manufacturers. Are there any Any questions from the group? Yes, that is true. So yeah, I saw Stephanie put in the chat that there's plastics for drain, waste and vent. That's pretty common, and copper for supply lines. I think your issues there is just going to be the issue of fire safety and fire stopping. Also in certain applications like commercial buildings where you might have a parking deck. The condo building where I live, for example, has a huge plastic waste pipe. I think it's for stormwater running straight through the parking deck. And when I park my truck right in front of it, let's say I'm a little tired one night, if I smash into that, it's not going to do well. So that might be something else to consider in that situation. All righty. Well, thank you. Thank you again for your time. I really appreciate it. And please do fill out the survey. I'd love to hear it. And if you have any other questions or follow-ups or anything like that, please email me or visit the website, and we'll go from there. Thanks again.